try and present from a laptop showing you the slides from here, it's going to be really, really small letters. So I don't know whether you're going to get much of the context. If you've got your own laptop, you can download the slides, try and follow on with me from there. I will try my best, and hopefully we can get somebody from the visual team to come back and do that. So I will try my utmost to try and just talk to you. A lot of the details are actually quite difficult to read on the slide anyway, and I can probably get most of the information across to you by just talking. So consider this some kind of weird improv type thing. But yes, yes. I think I'm sufficiently uncoordinated. I'll really fall over. Okay. So what was I intending to talk to you about today? If nothing else. So this sort of stemmed from a sort of adventure I had trying to cross-compile the compiler RT libraries of some various different versions of ARM. And I thought, after sort of going through the various bits of pain, trying to get CMake to work properly, which is actually probably the most difficult bit of the whole endeavour. And then sort of just saying, well, okay, how is this actually working? Why is this strange error message coming up? And I went on a bit of a deep dive into the driver to sort of work out how some of this actually works. But then tried to write some of this up. So I've submitted a new manual-like page on how to cross-compile compiler RT, which you can find on the LLVM documentation sort of side. So I thought, okay, I've done all of that work. Can I generalize that, put it into a presentation and try and talk to you? I think I sort of found that after investigating this for another couple of weeks, I think I knew less when I came out of the 2 weeks than I did when I went in. But I'll try and do my best to try and get at least across some of the general principles of cross-compilation and how it works within Clang and LLVM. So, first thing I'm going to start with is some definitions of what I'm going to use. For those of you at the back, I've said there's a host, and that's when I apply the host system, that's the sort of one that you're running the compiler on. The target is the sort of system that you're cross-compiling for. So the most typical example would be your host is x86-64, your target is some embedded microcontroller, something like an ARM type of thing. Oh, by the way, yeah, I'm using ARM and AR64 a lot. Is currently working for the Nauru. That's what I'm familiar with. A lot of the same principles that apply to other architectures as well. That sort of thing. I'm just using what I'm familiar with. Okay. So if I ever say the word native compilation, I mean the host is the same as the target. If I say cross-compilation, I mean the host is different from the target. If you look at the configure build system, they've got a separate host target build that's separate again. But I'm not going into that amount of level of detail. That's sort of where you have you're building a compiler on one architecture that runs on a different architecture that cross-compiles for a different architecture. That's the thing. It's all even more complicated. Okay. So why might you want to go through the pain of cross-compilation? What I'm telling you here is it's all a big nightmare. Well, the whole reason for it is that there's one scenario where it's even more of a nightmare compiling natively, and then there's another scenario where it's your only option. So, for example, the device on the top that I've got here is a picture of a Raspberry Pi. You can run GCC, you can run Clang on a Raspberry Pi. If you want to try compiling, say, LLVM and Clang on a Raspberry Pi, you're in for a whole load of pain. It will take an awful long time. Running the test suite, for example, will take several hours. So if you can cross-compile that on a very, very fast x86 server, you can get your build times down, you can iterate more quickly, that type of thing. So the first reason you might want to do cross-compilation is just that it's so much faster on a big server than it is on a small little device. For the device at the bottom, which is one of these BBC Micro bits, it's a Cortex M0. It's got about probably less than 64K on the actual board. There's no way you're going to run a C compiler on that. So some cross-compilation is your only option there. And similarly, as you know, that's one of the targets say you can't run a compiler on GPU yet. I'm sure they're working on it. Okay, so what I've got here is a diagram of some of the things that you might want to be considering concerned about when you're cross-compiling. So as well as actually doing the compilation itself, you've also got libraries, and this can be a simple embedded system. This is probably just static libraries that have been pre-compiled, or something a bit more complicated like a embedded Linux application. You might have shared libraries. Shared libraries are especially interesting in that it's very difficult to mix up static libraries on the host and target, but it's a lot easier to mix up shared libraries on the host platform and the target platform. You've got to make sure that you get those right. In particular, there's an option called RPath that you can give a link type, which basically says this is where you find your shared libraries. And when you're cross-compiling, you want the target to find your shared libraries to be valid on your target platform, not on your host platform. Otherwise, all sorts of things will go wrong at that point. Okay, so looks like in a few moments I've luckily got my slides on a little disk, so hopefully it will go across there. Okay. So may come back to that diagram later. Okay, thank you very much. Okay, so what have I got with this? Okay, so building, as I mentioned before, building an application is not just the compiler. You've also got to have a linker. You might also have to have other tools as well. In particular, you've got to convince your build system on your host to actually cross-compile, and that's actually quite often the most difficult step, because a lot of these systems have got tests to say, does your compiler do something sensible? And that initial check, does your compiler do something sensible, often tries to fight you at every possible step. So getting past that step is often the right.
View full screen.
Okay, yeah, thank you.
Some bottom.
Bottom.
What's the right bottom?
Thank you very much. Two slides here. Yeah, hooray! So one of the things I sort of thought initially, I thought, well, okay, let's just say what the cross-compilation options were and how to sort of put it through configure. And really, Clime's not really that much different from, say, GCC in that regard. So what I've sort of tried to concentrate here is what makes Climb different from GCC, and what are some of the things you might need to do to try and generate some of the libraries that GCC and Climb might use. So one of the interesting parts about Climb is that it has all of the targets compiled in by default. So if the Climb will come with your distribution, you can say target x86, target ARM, target MIPS, and it will produce an output for that. And that's, I suppose, probably less useful for the general developer if you've only got a small number of times. It's actually brilliant for a compiler developer, because one of the first things you want to do is say, what does this look like on this application? What's it look like this one? Can I compare the two? So that's really, really quite useful. But that also has a downside in that when you have a compiler that you compile at build time to target one thing, then the actual options, parsing your sort of options to get them set up properly are quite limited, and a lot of the stuff is based around that. Whereas in Clang, where it's sort of saying, well, I can cross-compile this architecture, I can try and take the Windows binary, that sort of thing. There's a lot more configuration options. Oh, okay, I'm sorry. So the people online got no words and no pictures. That's great. Oh well. Okay, right. Maybe I'll find some opportunity to repeat this. Okay. So first thing we have to do with Clang is actually tell it what to compile for. So when you type Clang on the command line, normally you're getting what's called the default target triple. Whereas when you're doing cross-compilation, you have to explicitly give Clang a triple, and it will, and I'll explain it will have a target triple on the other side. Now, one of the things about the LLVM project, I think that's just a ball and seat problem. Okay, right, I'm actually unlike, say, a GCC toolchain that you might, or cross-compilation toolchain that you might download, there's no such equivalent for LLVM as far as I know. There may be some companies that are attempting to bunch all of the libraries and everything up, but so far you can't just build the LLVM project and get, say, a C library, which is of course the most important missing component of that. You can get quite a lot of the tools from, say, just downloading the LLVM source sort of binary release, but you can't get everything. And there's also some of the library dependencies aren't there. So, for example, so here's my sort of kind of brief spreadsheet about what things are included with LLVM, what's the equivalence, that sort of thing. I've marked the bits in orange as, yes, these tools exist. They may not be as good as the equivalents. They're more sort of developer tools. If you sort of have a tool chain based on LLVM, you may not get those tools included out of the box. That's like the equivalent of FOSDEM, for example, which is what you would use to disassemble your binary. There's LLVM, but it won't disassemble the same way as InimWatch is. So typically, those tend to be aimed at developers and not for users. The most important missing part is the C library. So you have to replace that or find something to use when you plug in. The stuff that is in the box, obviously Clang is an equivalent for GCC. The assembler is not separate in Clang. Each target has its own. I don't know whether all in-tree targets have it built in the assembler. No. Okay. I think for the majority of the supported applications, that's actually the case. LLD is natively a cross-linker. It doesn't support all of the targets that are supported by Clang. If you are supported, your inflow should work for you that particular bit. LibOnWine is a Untitled Library that's equivalent to the GCCS in the real world. libc++ API, libc++, equivalent libc++, so it's still C++. Typically, as a sort of end consumer thing, you kind of pretend that those libc++ API and libc++ don't exist. They're kind of the implementations of new and delete and the sort of mechanics of doing exceptional winding. They're not the standard library, whereas libc++ and C++ are the standard libraries. You would think that's where the STL contract is.
There's also the GCC EH, which is in with C++ API.
Right. There's probably lots of detail below the iceberg there. Okay. So one of the first things you have to do when you're using Clang as a compiler is you have choice. Choice can be a good thing or a bad thing. If you don't care, best stick to the defaults. So typically what will happen is on a sort of Linux targeting system, you'll end up with defaulting to the GCC components. So even if you have built compiler RT, by default, Clang will look for libgcc at that particular point. Now, that actually makes quite a lot of sense if you're targeting a Linux system in that libgcc will already be, and various other Linux or GNU-like dependencies will already be on your system. So unless there's a particular reason for you to want to prefer the LLVM versions, it's best to stick with your platform default, but you can obviously make those certain choices there. So I won't bother reading out the whole slide on there. But certainly, this sort of C library choice can affect the sort of target that you use. Okay. So I promised I'll get on to the target triples. This is perhaps the most important user option in my case when you're doing cross-compilation. So I say triple, but it's obviously way more than 3. You can count from there. It's really kind of more of a tuple than a triple. I believe it's called a triple because it was based on the original configure triples. It's sort of kind of grown out from there. So the most important one, I think, is definitely Arch. So that would be something like ARM, NIPS, that type of thing. Subarch is kind of, I'd say it's mostly an ARM thing. I think there's one other architecture that has a subarch. But this is where you do things like ARM v7m or Cortex-M0, ARM v7a, Cortex-A, and Cortex-A15, that type of thing. So typically you don't have subarch. One of the things we've got, if you miss any of these out, you'll get a default option, which may or may not be what you want. Vendor is typically not used. It's often actually where a lot of proprietary vendors that say are building their own tool chain out of LLVM will use that mechanism to select your driver. So say, for example, if you've got a consultancy company X, you would say something like the triple will be on dash consultancy company X dash whatever, and they would use that to put any particular driver replacement things for things. OS is your target operating system, where non typically means bare metal. Obvious things there would be things like, say, you might want to target FreeBSD, NetBSD, whatever, or Linux, that kind of thing. And that's the final environment. Will also tend to determine the ABI and the object file format that you choose. So, for example, on a Mac, which the object file format is Mac-O, you can generate an ELF file by putting in the right triple, that type of thing. But of course, you've got to be careful to choose the right one for your target. And one of the things that thing does is choose what toolchain class in Clang. So I'm sort of deep diving a little bit into the implementation details of Clang here, in that I think if you try and do any bits of cross-compilation, you're stuck. And trying to work out what Clang does, the fastest way to resolve what it's doing is to go look into the toolchain class and look at what it's doing. It's sort of oh, this must be documented somewhere, and no, I couldn't find it. And I thought, well, surely I can just document it and put it in the slides. And then I looked at it and went, I don't know whether anyone could document this. It's kind of there's lots and lots of different things. So, for example, there might be things like, I need to find this particular library. Oh, let's try this particular directory because this is what it's like on Ubuntu. Oh, SUSE puts it in this directory here. And it's just this big tree of things that might be to find things out. But generally, what happens when you call Clang? What it will do is it will parse these options, select what kind of driver it wants to go for, and then it will invoke the various programs as sub-processes. So, for example, CC1 is the actual C compiler, CCC1AS is the integrated assembler, LLVM is a link to a separate program. So if we say the architecture for target AR64 Linux GNU, that will select the Linux toolchain. And if we try and do things in the Linux way, so for example, you've got things like -I system Clang will put in where it finds your input class there. On the linker, it will select the right target based on that sort of thing. So that's kind of where this is the target triggers all these various things here. And you can get at these options here with the sort of I think the dash. I've got it written down. I don't know whether it's got a name. It's a dash and then 3 what British people will call hash symbols. I think Americans call pound symbols. So someone, a friend of mine back at work, actually called it the toilet brush operator. Yeah, chimney sweep or something like that. But anyhow, I find that the easiest way to remember what it is. So just a few of the things that I've mentioned there, I won't go through that again. Driver mode is kind of tells you how the Clang will try and add extra include files, change its personality. Most important one on there, if you're a Windows user, is CL. If you do that, it will try and emulate the command line options of Microsoft Visual Studio and switch to outputting in the way compatible with Microsoft Visual Studio. I'm assuming it's FOSDEM, that's not of interest to you, but that's not so the most important thing for us here is to use Clang++ if you're compiling C++, otherwise Clang will miss out some of the header files and includes, and you'll get things like it cannot find IO stream type things, which if you get that and you think it should just work, there's chances are you've used Clang rather than Clang++. And manually say -- driver mode as well. That's so one of the things that you might find is that progress is interesting. So what I wanted to do here was just go through some of the steps that you might want to go through for building a simple application targeting an AR64 Linux thing. So what I chose to do was to use compiler RT, which is the runtime library. It's also where the sanitizers we've implemented. I'm going to use undefined behavior sanitizer, mostly because the memory sanitizer and the address sanitizer don't work with the Kremlin user mode emulator. Because they muck with page tables in very nasty ways, and the Kremlin user mode emulator is not really set up to do that kind of thing. So I'm using the Kremlin -AR for user mode emulator, just a simple way of testing it on it. Typically you would deploy it to a device. So that on my shopping list is the tools that I'm going to need to do to make this work. Okay, so how do you actually get these components? So if you don't want to build everything from scratch, then the simplest way to do this is to go and download one of the LLVM releases. If you're going to do this here with the sanitizers, you're going to have to be careful, because if you download the x86 release, you'll get x86 binaries of Clang that can cross-compile to AR64. But the sanitizer libraries will be x86 sanitizer libraries, and you won't be able to run those on an AR64 target. If you download the AR64 release, you'll have an AR64 Clang that you won't be able to run on an x86 host. So you'll have to sort of combine the bits from two if you want to make a sort of full cross-compilation switch. We'll also have to find C library and other various dependencies. It's just two potential ways to do it. If your Linux distribution supports multi-arch, then that's usually a very safe way to go. I use the Linaro binary toolchain release, which is kind of like a directory that has a sysroot with all of the libraries that you generally need, plus the utils and GCC that type of thing. I use that mostly to sort of just show the differences. One of the sort of if you're sort of in a production environment, multi-arch might not be a stable way to get repeatable builds on different people's machines. So some people prefer to download everything into one directory so that they can be sure what they're using. Okay. So I won't go through all of that. That's mostly saying, here's where to download the Linaro toolchain, how to install it, what it is, that type of thing. Different GCC toolchains might have a slightly different layout than the Linaro toolchains. The things that I've written here, you may need to experiment around with it. So one of the things that I mentioned before about is the runtime libraries. So typically in the compiler you've got various different locations that will look for various directories. So Clang has something called resource-dir, and that's where it will look for what you would call compiler-specific libraries. I think I'm not an expert on this particular distinction, but my understanding is it's kind of libraries that, or include files that depend heavily on the implementation of the compiler go in this particular directory, as opposed to, say, the standard sort of include directories. So I think you can print that location directly out, but I don't think you can change it to the command line options by the Clang group. You can pass in a developer level command line option to do it, but I wouldn't recommend that to start with. Okay. So I've just mentioned there about if you're going to plug in the compiler RT sanitizer libraries, they need to be in this big long directory with the list. So here's the application I've got to compile. So basically all I've done is I've taken a UBSAN example application and I've just added a spurious exception just to show that I can throw an exception. It doesn't do anything useful, but what we want is the UBSAN this sign integer overflow. The exception is there mostly because if we don't get to there, then we know that exception handling is not already gone. So here's what I did, assuming everything was all put together. I know it's going to be very difficult to read at the back. It's probably something that's best looked at offline. But I just want to highlight some of the options that I've used. So obviously for the select sanitize, X-sanitizer, fine. The ones that I found the hardest to get right were the sysroot option and the GCC toolchain option. Now, in theory, sysroot is all you need. What the sysroot option is basically saying, find your include files relative to this, and libraries relative to this directory. So I pointed this in my pre-downloaded Linaro toolchain directory. So why do I need GCC toolchain again? And what this --GCC toolchain is doing is kind of saying, I want you to start your search for a valid GCC from this location, because Clang has sort of various heuristics for trying to find the tools. And one of the things it can often do is it can say, oh, I can't find various bits of the sysroot that I'm looking for in this particular location. I know, I'll try /USR. And sometimes it finds a program called LD, and so it'll often find the host linker, which then spits your AR64 binary out because it doesn't understand it. So really, what that GCC toolchain there, it's sometimes necessary, sometimes not. I tend to use it just to be absolutely sure it's going to pick up the GCC toolchain.
So a quick comment important about that is that you should really use both GCC toolchain and sysroot, because GCC has build time configuration, and the sysroot can be in slightly different ways depending if it's Debian, Ubuntu, CentOS, or even the model.
Yeah.
So you should use both.
So yeah, just at the bottom there, that's just using Qemu yes, in principle, the UV sound can work on Qemu using the user mode emulator. So for those of you not familiar with the user mode emulator, what it's doing is it's intercepting the system calls from the target and then emulating them on the host. So that's why it can't handle NSAM and ASAM. Okay. So this next few slides I'm going to go through pretty quickly. This is basically what would you do if I want to compile libc++, libc++ API myself. I think it's getting better and it's a moving target, which is often where I think there's a lot less documentation about this than there perhaps ought to be. All I can say is that it's a bit of a, you kind of have to make sure that you know exactly what you want to build. You need to know exactly what dependencies that you want. If you just say, for example, build libc++, you'll probably find it gets built against the GNU libgcc, for example, by default. You actually have to go into this tell it that you want to build against compiler RT. And that's the same sort of thing. And you'll notice that there are various different dependencies between the components. So what I found the easiest way to do was to build all of these components standalone. And by standalone, I don't mean check out them all in one very big directory as the use of LLVM build instructions will tell you for a native build. But what I do is build each component individually by pointing the CMake to the specific CMake file rather than the sort of top level one and expect it to always work it out for me. So just some hints and tips that I sort of found out along the way. So one of the interesting bits that I really wish I'd known about earlier is that most Clang binaries are called Clang. If I rename that to AR64-Linux-GNU-Clang, Clang would automatically infer the target of AR64 Linux GNU, and I wouldn't have to put --target in all over the place. So that's just a simple name of the file convention that you might find useful.
Symlinks.
Yeah,
You can do any number of symlinks and it will work.
Right, okay, that's also good to know. And there's a very recent, I don't know whether this made it into LLVM 6, it will certainly be in LLVM 7, but they've just introduced something called the config file, where you can sort of say, collect all of these cross-compilation options up into a config file, and it will just get automatically selected. And there's a similar file naming convention where you can kind of name your config file as a prefix of the executable, and it will automatically pick it up so you don't have to say it all over the time. As I say, Clang-B is great for trying to debug what it's sending to the linker. So if your linker spec is failing, use the --B option and you can see exactly what files it's sending through. I've mentioned this toolchain and sysroot. As I mentioned earlier, when using shared libraries, we make sure the host and target ones all line up. The CMake cross-compilation, I found the most difficult. I found targeting a Linux platform that I could use that had a link support that worked quite well. So, for example, if you've got the cross-compilation for linking for AR64 Linux and ARM Linux, that's actually pretty simple. try to do that for, say, a Cortex M0, where you've got to give the linker huge amounts of extra flags. It's a real pain. So recent options variants in CMake have got things saying CMake try compile target, you can stop it driving, and it won't do the link step, which is really, really useful if you're just building a static library and you've never touched the linker. That's one way of basically getting past that sort of code. Print search does, it's really, really interesting if you want to find out what various different system options are actually going to include. So, conclusions, Clang can work well as a cross-compiler. Because of the number of different options that it's got, you have to tell it more than you would do to an equivalent GCC. There are defaults there. I would say the path of least resistance is to use the ones that are native to your system. So if you're targeting Linux, it's easier to, you'll make your life easier if you can target the new versions at that point. The bare metal driver, I've got some backup slides of my experience trying to build some bare metal stuff, but that was a whole new story and probably take another hour's worth of presentation, so I haven't gone through that, but I've put some stuff in there. But that's all I have to say for now. We've got a very small amount of time for questions. I know they're 2 minutes, so yeah. So that, yeah.
So I've got one question and one remark. The question is, you set off at the start to use a mostly or exclusively LLVM-based toolchain with LLD and Clang. So why does it still need the GNU toolchain?
So it uses, in that particular example, I didn't use any of the GNU tools, but I used some of the GNU libraries. So for example, I used the GNU C library at that particular point. And at the moment, there isn't any plans to have a replacement for that point. But if you're on a different architecture, you might not have a linker in the LLVM program, so you might use the GNU tools linker. Sometimes the same. Okay. Anybody else? We've probably got one time.
When cross-compiling, I didn't follow the latest LLVM development. Is there progress in compiling the floating point? Because if you're now using, for example, double on PowerPC or extended floating from Intel, you have trouble if you're hosting environment, that's what you told us.
Sorry, I haven't gone there either. Sorry. If anybody does know about any recent developments in floating point compilation, I'm sorry, I'm not. I think we probably best wrap up for the next.